All right, now I'm going to look at an example of taking powers and roots using cis form, or cosine I sine form. And what we're really going to be using here is something called DeMoivre's theorem, which is basically an outgrowth of the multiplication and division process. If you remember, you multiply the lead coefficients, you add the angle measures, okay? So if you're taking something to a power, you'd be multiplying it by itself 3 times. Those leading coefficients would get multiplied. You'd have 5 times 5 times 5, which is really 5 cubed. Okay, you're really just going to be taking that value to the 3rd power, okay? With the angle measures, you would have each of these and you'd be adding those. And what that means is we would get each of these angles 3 times. So you'd have 3 of these and you'd have 3 of those. And as a result, 5 cubed, of course, is 125. 3 times pi over 6 would be 3 pi over 6, which is really pi over 2. And then, of course, you've got the same angle there, so you've got plus I sine of pi over 2 there as well, and that's your final power. So that's essentially the takeaway from DeMoivre's theorem. Okay, the follow-up here, and this is a little bit more of a challenge. If you're taking roots of complex numbers, and do watch the book directions, a lot of times they'll just ask you for the primary root, which would just be the basic one, applying the relationship. So let's say I wanted to take the cube root of 8 cosine of pi over 2 plus sine of pi over 2. And by the way, just to recognize what that value is, that's at an angle of 90 degrees, and it's got an absolute value of 8. So that's actually the number 8i. Remember, you've got a real axis and an imaginary axis, and that's how that would pop up. So we're really looking for the cube root or cube roots of 8i is essentially what's happening here. And the idea here is you want to apply DeMoivre's theorem. A cube root is the same thing as taking something to the 1/3 power, okay? So really just rewrite this as a 1/3 power, and on the surface, you just apply DeMoivre's theorem. So DeMoivre's theorem says you're going to take 8 to the 1/3 power, and again, you just need the primary, whatever the primary root is. The 1/3 power of 8 is just 2, okay? So you've got basically 8 to the 1/3 power, and then each of these angles is also getting multiplied by the exponent. So you're taking 1/3 of pi over 2 in both of those cases. So 8 to the 1/3 power is 2. You're going to get cosine of pi over 6. You're dividing the angle measure by 3 plus I sine of pi over 6. And of course, if you needed to, you could graph that and you could convert that back over into rectangular form if you wanted to find out what that complex number looked like in a more standard form. Okay? The follow-up to this, if I ask you for all of the cube roots, remember when you're talking about roots, there should be 2 square roots of a number, there should be 3 cube roots of a number, there should be 4 fourth roots, and so on and so forth. And this is all an outgrowth of the fundamental theorem of algebra. The big idea here really comes back to coterminal angles. And so, for example, if you have an angle measure of pi over 2, you can add 2 pi to that, and that would give you 5 pi over 2, 2.5 pi, okay? And that would be another angle measure that would basically graph in the same position, would be coterminal, and you could find that value. So if you did 5 pi over 2 as your angle, if you're taking 1/3 of 5 pi over 2, that would give you 2 cosine of, that'd be 5 pi over 6 plus I sine, and then you're going to get another 5 pi over 6. And so that's your next angle measure there, okay? And you can add another 2 pi to this. If you take pi over 2 and you add 4 pi, you're going to end up getting, let's see, that's 8 halves. You're going to end up with 9 pi over 2. That's 4.5 pi, okay? So if you had 9 pi over 2 and 9 pi over 2, you're going to end up with 9 pi over 6, which is 3 halves, right? So you're going to get 2 cosine of 3 pi over 2 plus I sine of 3 pi over 2. Not sure, that may have gone off the screen there. Not sure how low my camera is. But that's your basic idea, okay? So that's something to kind of keep in mind there as well. Now, if you want to put all this together, do a little racing here. If you want to put all this together, what did we just do here? Well, the interesting thing that comes out of this is that the roots are always going to be evenly located around a circle from each other. In other words, if I were to graph this, 2 cosine of pi over 6, pi over 6, that's a 30-degree angle there, right? So it would be 2 units out at a 30-degree angle, okay? 5 pi over 6 is 150 degrees. So that's over here, 2 units out. And again, that's at a 150-degree angle. Notice there's 120 degrees between a 30-degree angle and a 150-degree angle, okay? 3 pi over 2, that's 270. So you're going to go 2 units down at 270. Well, guess what? There's another 120 degrees between that. There's between 270 and 390, which is essentially what 30 is, there's another 120 degrees. So they're evenly spaced around a circle. So a fast way to do this, you can actually find the principal root, and then you can really just divide 360 degrees or 2 pi by the number of roots you want, and that'll tell you how much you have to add each time. So like in this particular case, 360 divided by 3 is 120 degrees. So if you got one at 30 degrees, you had 120. You've got one at 150. You had another 120. You've got one at 270. If you had 4 roots, 390 divided by 4, I'm sorry, 360 divided by 4 is 90. And they would be 90 degrees apart all the way around the circle. So you don't necessarily have to do all this work with these coterminal angles. Basically, you're going to add 180 degrees each time if you're looking for 2 roots, and they're just going to be opposite each other on a circle. 120 degrees apart if you have 3 roots, 90 degrees apart if you have 4 roots, and so on and so forth. So there are examples of this in the book, but I thought it might be helpful to actually see that on a video, so hope that helped.